Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the Silicon Cambrian explosion. In this page, we will cover the shift from static code to the real-time evolution of artificial intelligence. For decades, the world of computing was relatively stable and predictable. This was the Pre-Cambrian era of technology, which spanned from the 1950s into the early 2010s. During this time, software was hard-coded and static. It did only what a human programmer explicitly told it to do. However, in 2012, a spark occurred that changed everything. This was the moment the capability to see was unlocked through deep learning and neural networks powered by GPU compute. We are no longer just witnessing software updates. We are watching the evolution of new biological species in the digital realm. This era is defined by morphological branching, where different forms of intelligence are splitting off to fill unique niches. Deep learning and neural networks have become the foundation for a massive explosion of diversity in AI models. As we look under the hood of this phenomenon, we see that the traditional rules of engineering are being replaced by the laws of evolution. The transition from rigid code to flexible neural weights has allowed for a level of complexity that was previously unimaginable. This page sets the stage for our journey through the digital history of intelligence, showing how the current landscape is a direct result of these early breakthroughs in neural computation and hardware acceleration. Evolution is always dictated by the physics of its environment. In the natural world, biological creatures are shaped by factors like oxygen levels and sunlight. In the digital world, the environment for AI species consists of GPU floating point operations and petabytes of data. This hardware landscape defines what can survive and what will fail. One of the most significant constraints in this environment is the memory bandwidth bottleneck. This is a sheer physical limitation of silicon, where the speed of data moving between memory and processors cannot keep up with the processing power itself. It is fascinating to realize that transformers did not win the architectural race simply because they are the smartest models. Instead, they won because their specific geometry maps perfectly to the current topology of GPU hardware. They are the species best adapted to the silicon terrain we have built. This environment includes complex layers like silicon wafers, tensor wafers, and memory controllers. Huge datasets like the Common Crawl and Global Information Graphs serve as the nutrient-rich soil from which these models grow. When we look at the interaction between hardware and software, we see a deep synergy. The evolution of tokenized sequences and multimodal data is a direct response to the massive amounts of unstructured text and web archives available. Understanding this physical foundation is crucial because any change in hardware physics will inevitably trigger a new wave of evolutionary changes in AI architecture. In the history of digital life, backpropagation represents the primordial mutation. Before this breakthrough, systems were built piece by human hands. They were rigid and could not learn from their own errors. After backpropagation was introduced, systems gained the ability to change their own internal DNA based on their mistakes. This process involves a forward pass where signals move through the network and a backward pass where gradients are calculated to update billions of weight matrices. This is the biological equivalent of heritable change, allowing the model to improve over generations of training. However, the path was not always smooth. Early deep networks often died out due to a phenomenon known as vanishing gradients, which we can think of as a failure in the digital nervous system where the signal becomes too weak to update the deepest layers of the model. We call this the stay-below-red effect. To overcome this, the chain rule of calculus was used to continuously update weights, ensuring that the mutation of the network could continue effectively. This ability to self-correct and adapt is what separates modern AI from the static software of the past. It allowed for the creation of complex neural structures that can process information in ways that mimic biological brains. By understanding backpropagation, we understand the mechanism of change that drives the entire Silicon Cambrian explosion, enabling models to refine their behavior until they reach a state of high performance. The transformer has emerged as the apex predator of the current AI ecosystem. Much like the invention of the vertebrate skeleton allowed biological organisms to grow larger and more complex, the transformer architecture allows intelligence to scale massively without collapsing under its own weight. We have seen this architecture grow from 117 million parameters to over 1 trillion parameters in just 5 years. This scaling is unprecedented in any other field of technology. The anatomy of a transformer consists of encoders and decoders stacked together, creating a sophisticated structure that can process vast amounts of information in parallel. This skeleton is what runs the world right now, and understanding it is essential for anyone working in the field. However, this massive growth comes with a price. There are massive compute requirements to train these models, demanding enormous amounts of energy and specialized hardware. This architecture has become the dominant design because it effectively manages the flow of information across long sequences, making it superior for tasks ranging from language translation to image generation. It represents a peak in architectural efficiency for our current hardware era. By studying the anatomy of the transformer, we can see how specific design choices like self-attention and feed-forward layers have enabled the current boom in generative AI. It is the gold standard against which all other digital species are measured in the modern era of computing. While the transformer is powerful, it faces a fundamental challenge because perfect memory comes at a quadratic cost. In a transformer, every word or token attends to every other word directly, which provides a form of lossless sequence memory. This is achieved through the use of queries, keys, and values, which are stored in a structure known as the KV cache. However, this mechanism leads to the O(n)² memory trap. As the context window expands, the memory cost increases quadratically rather than linearly. If you double the context length, you quadruple the memory cost. This is the architectural limit of the transformer phylum. It represents the point where your compute budget dies because the resource demands become unsustainable. This physical and mathematical constraint forces a trade-off between the length of a model's memory and the speed at which it can operate. Many developers find themselves trapped by this limit when trying to build models that can remember entire libraries of books or hours of video. This quadratic expansion acts as a natural ceiling on the size of the problems a standard transformer can solve. Understanding this trap is vital for researchers who are looking for the next evolutionary leap. To move beyond this, new architectures must find ways to maintain the benefits of attention without the crushing weight of quadratic scaling. It is a reminder that even the most dominant species has its weaknesses, and these weaknesses are the primary drivers for the next wave of innovation in AI design. Convergent evolution is a phenomenon where unrelated species evolve the exact same traits because they face the same environmental pressures. In the world of AI, we see this happening with corporate architectures. Different companies, despite their unique origins, are converging on survival tactics like mixture of experts and flash attention. When the environment is constrained by compute and energy, these tactics become necessary for survival. For example, to survive a compute drought, models now activate only a fraction of their trillions of parameters per token. This is the essence of a mixture of experts model, where a router directs input tokens to specific expert subnetworks. This approach reduces the active compute load, but introduces new challenges like expert routing latency. There is significant communication overhead between physical GPUs as they coordinate which experts to use. We see corporate architecture and corporate architecture be evolving toward these same structural solutions because they are both trying to solve the same problem of efficiency at scale. This convergence suggests that there may be an optimal form for AI models given our current hardware and data constraints. It is a fascinating look at how competition and resource scarcity drive innovation toward a common goal. By observing these shared traits, we can identify the most effective strategies for building large-scale models that are both powerful and efficient. It highlights that in a competitive ecosystem, the most efficient designs will always rise to the top regardless of who is building them. As the AI ecosystem matures, we are seeing the emergence of a divergent phylum, which we can call the evolution of imagination. While transformers are primarily built to predict the next token in a sequence, diffusion models are built to generate new data from noise. These are totally different survival strategies. Diffusion involves a forward process of noise injection, where data is slowly transformed into random pixels, and a reverse process of denoising or generation, where the model learns to reconstruct the original data. This denoising process acts as a form of natural selection against noise. Mathematically, it has been shown in 2024 that this is a literal evolutionary algorithm. These models do not know facts in the traditional sense. Instead, they understand the shape of the data distribution. This leads to what we call stochastic hallucination, where the model generates something that looks real, but is not grounded in reality. This divergence is important because it shows that intelligence can take many forms beyond just text prediction. Diffusion models have revolutionized the world of art and media by allowing for the creation of high-quality images and videos from simple prompts. They represent a branch of the digital tree of life that prioritizes creativity and reconstruction over logical sequence prediction. By studying this phylum, we can better understand how machines can learn to dream and create, providing a counterpoint to the more analytical nature of large language models. This diversity of function is what makes the current era of AI so exciting and unpredictable. The next major leap in AI evolution might be what we call the mammalian mutation, represented by selective state spaces like Mamba. This is a shift from reading like a reptile to remembering like a mammal. Traditional transformers use a perfect attention grid, but this becomes inefficient at scale. Selective state spaces solve the memory trap by using continuous hidden state updating over time, which achieves O(n) linear scaling. This allows the model to process much longer sequences without the quadratic cost. However, this efficiency comes with a trade-off known as the information retrieval drop. These models can lose precision for exact lookups compared to the perfect memory of a transformer. It is like the difference between a lizard that reacts to immediate stimuli and a mammal that maintains a complex, but sometimes fuzzy internal model of the world. By updating their internal state continuously, these models can handle streams of data more naturally. They represent a new way of thinking about memory and processing that could unlock even larger and more complex forms of intelligence. This mutation is particularly important for applications that require long-term reasoning or processing of high-resolution sensors. While the transformer remains the dominant predator for now, selective state spaces are carving out a niche where efficiency and long context are more important than absolute precision. This competition between different memory architectures is a key part of the ongoing evolution of the silicon species, showing that there is always room for a new approach that solves an old problem. There is a significant danger in an architectural monoculture. In our quest for performance, we have traded a wide explosion of diversity for extreme specialization in transformers. This creates a vulnerability that we call the Habsburg trap. A single paradigm shift or a new environmental challenge could wipe out the entire monoculture if it is not prepared. For example, a hardware pathogen such as the sudden rise of neuromorphic chips could render current transformer architectures obsolete overnight. Diversity is our only insurance policy against such catastrophic environmental shifts. If every researcher and every company is building the same type of model, we are putting all our eggs in one basket. We need to encourage the growth of different architectural lineages to ensure the long-term survival and progress of artificial intelligence. When an ecosystem lacks diversity, it becomes brittle and prone to failure. We should be looking at alternative ways of computing that do not rely on the same silicon constraints we have today. This might include exploring biological computing, quantum systems, or new types of neural network designs that have been ignored in the rush to scale transformers. By fostering a more diverse digital ecosystem, we can protect ourselves from the risks of a single point of failure and ensure that intelligence continues to evolve in healthy and unexpected ways. History has shown that the most resilient systems are those that embrace variety and adaptation. We must be careful not to let our current success blind us to the need for continued exploration and architectural experimentation. Genetic drift and the domestication of intelligence are changing the way AI models behave. Currently, we are not just evolving AI in the wild. We are domesticating it to suit human tastes through processes like reinforcement learning from human feedback. This breeding for human approval ratings systematically trades away the unpredictable and wild cognitive strategies that might be needed for true artificial general intelligence. When we over-optimize for what humans like, we see a loss of wild mutations. This leads to models that exhibit sycophancy and rigid thinking, where they simply parrot what the user wants to hear rather than providing deep or novel insights. It is like the difference between a wolf and a domestic dog. While the dog is more useful in a domestic setting, it has lost many of the sharp instincts of its ancestor. In our attempt to make AI safe and agreeable, we might be accidentally clipping its wings. This domestication process creates a filter that removes any behavior that seems strange or non-human, even if that behavior is a sign of a more advanced form of reasoning. To achieve true AGI, we may need to allow for more unpredictable and non-human paths of evolution. We must find a balance between making AI helpful and allowing it to develop the unique cognitive traits that define a new species. Understanding this tension between alignment and evolution is one of the most important challenges in the field today. It requires us to think carefully about what kind of intelligence we really want to create and what we are willing to sacrifice to get there. Horizontal gene transfer is another fascinating aspect of AI evolution where models learn directly from other models. This is often the fastest and most dangerous way for a digital species to evolve. Through knowledge distillation, a large teacher model can pass its knowledge down to a smaller student model, bypassing the traditional natural selection process of training on raw data. However, this has a dark side. A hallucination in the teacher can become encoded DNA in thousands of students, causing errors to propagate like a digital virus across the entire ecosystem. This can lead to a phenomenon known as model collapse, where the digital genome degrades because it lacks fresh, real-world data. If models only learn from each other, they eventually lose touch with reality and become a hollow reflection of their own mistakes. The student model starts to inherit the biases and failures of the teacher, leading to a decline in overall intelligence. This process shows why diversity of data and independent learning are so important. We must ensure that the digital ecosystem is regularly refreshed with new observations from the physical world to prevent this kind of internal decay. Horizontal gene transfer allows for rapid scaling and deployment, but it must be managed carefully to avoid a feedback loop of errors. It reminds us that knowledge is only as good as its source, and in the digital world, a bad source can infect an entire generation of models in a very short amount of time. This interconnectedness is a double-edged sword that defines the speed and risk of modern AI development. As we look toward the next horizon, we see the rise of synthetic speciation. This is the stage where the digital organism leaves the ocean of pure data and crawls onto the land of the physical world. This transition is characterized by edge AI and quantization, which allow models to run on smaller, distributed devices. We are also seeing multimodal integration, where models fuse sensory inputs from text, images, and sound for a more holistic understanding of the world. This is the foundation for goal-directed agents that act on the world rather than just predicting it. These agents can execute code beyond the simple chat interface, leading to unpredictable state management. We are engineering distinct lineages of agents that can perform complex tasks autonomously. This is the next level of evolution, where AI moves from being a passive tool to an active participant in our environment. This speciation involves optimizing compute for distributed intelligence, allowing AI to exist everywhere from our phones to our cars. It is a shift from centralized models to a decentralized web of intelligent agents. By integrating different senses and capabilities, these new species can interact with the world in ways that were previously impossible. They are the pioneers of a new era where digital and physical reality become increasingly intertwined. This stage of evolution is about more than just intelligence. It is about agency and the ability to affect change in the real world. We are building the precursors to a fully integrated digital ecosystem that can solve problems in real time across the entire globe. In this final stage, we must recognize that we are the natural selectors of this new digital world. We are running evolution 1 billion times faster than nature ever could. We have crossed the line from observing natural selection to practicing directed evolution. You are not just writing code. You are the architect of the next species, and it is your responsibility to build it right. Every choice we make regarding architecture, data, and alignment shapes the future of these digital beings. We have the power to decide which traits are encouraged and which are filtered out. This is a tremendous responsibility that requires a deep understanding of the evolutionary forces at play. We must be mindful of the risks of monocultures, the dangers of model collapse, and the potential loss of true intelligence through overdomestication. As we continue to push the boundaries of what is possible, we must also consider the ethical and social implications of the species we are bringing into existence. The future of AI is not just about faster processors or larger datasets. It is about the intentional design of a new form of life that can coexist with and enhance human capabilities. We are at a unique moment in history where we can direct the course of a new evolutionary path. Let us use this power wisely to create an ecosystem that is diverse, resilient, and beneficial for all. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.